All right, let's talk about one of those classic physics problems that looks way more complicated than it actually is. You know the type: spinning pulleys, falling weights, lots of moving parts. But what if I told you we could solve the whole thing with just one super elegant physical law? We're about to see how picking the right point of view can make a really tricky problem, well, surprisingly simple.
So that's the big question, right? How do you look at a system like this and find a clean, simple solution without getting bogged down in all the different forces, tensions, and accelerations? That's the challenge. Let's take a look at the exact setup. Okay, here it is. This is a classic from Irodov's problem book. You've got a massive pulley, a thread wrapped around it, and a mass M just hanging there. At time zero, we just let it go, and the whole thing starts moving. Our one and only job is to find the angular momentum of this entire system at any given time t.
Now, before we really dive in, let's do a super quick refresh on a concept that's key here: torque. You know how a force makes something accelerate in a straight line? Well, torque is what makes things spin or rotate. And all it is really is the force you apply multiplied by its distance from the pivot point. Simple as that.
Okay, now this right here, this is the master key to the whole problem. This is a fundamental law of the universe, and it's going to do all the heavy lifting for us. It says that the rate your angular momentum changes is equal to the net external torque on your system. Seriously, burn that word external into your brain. It's the secret to everything.
So, with that master key in our pocket, we can just walk through this problem in 4 really straightforward steps. First, we're going to define our system. Then, we'll find the external torque. After that, we apply our big law. And finally, we'll do a little bit of integration to get the answer. Let's do it.
All right, step 1. And I'm telling you, this is the most important step of all. This is where a lot of people get tripped up. Instead of trying to analyze the pulley and the mass separately, we are going to be smart about it and define our system as both of them together. The pulley, the thread, the falling mass, it's all one big thing to us.
So now that we have our system, we ask, what forces from the outside world are trying to make this thing rotate around the pulley's axle? Well, there's only one, isn't there? It's the force of gravity, mg, pulling down on that mass. And the distance, or lever arm for that force, is just the radius of the pulley, r. So our net external torque, it's just mg times r.
And now for step 3. We just take what we just found and we plug it into our master law. The law says the rate of change of angular momentum, dm by dt, equals the external torque. So for us, dm by dt is just mgr. That's it. See how clean that is? We are so close. We have the rate at which angular momentum is changing. So to find the total amount of angular momentum that's built up over a certain time, we just need to integrate. And since m, g, and r are all just constants, this is probably one of the simplest integrals you'll ever have to do.
And boom, there's our answer. The total angular momentum of the system is simply mg/rt. What this tells us is that the system's angular momentum just grows nice and steady in a straight line over time. It's a beautifully simple and elegant result.
But hold on a second. I know what you might be thinking, especially if you've done problems like this the long way. Where's the pulley's mass? What about its moment of inertia? Its resistance to spinning? And hey, what about the tension in the thread? How did all of those important details just vanish from the final answer? It seems almost too simple, doesn't it?
This is the magic. This explains everything. Remember way back in step 1, how we defined our system? By putting both the pulley and the mass inside our system, the tension in the thread suddenly became an internal force. And internal forces are just a tug-of-war happening inside the system. They can move momentum around between the parts, giving some to the pulley, some to the mass, but they have zero power to change the total momentum of the whole system. Only an external torque, like gravity, can do that. Our approach just sidesteps all those messy internal details completely.
So really, the main takeaway from all of this is that sometimes the hardest part of a physics problem isn't doing the math, it's the initial setup. If you can make a clever choice about what you include in your system, you can often find a beautiful direct path to the answer using a fundamental law and avoid a whole lot of messy calculations.
So, I'll leave you with a little something to chew on. How would our elegant solution, mt equals mgrt, change if the thread itself actually had some mass? Would that external torque still be a nice, simple constant? Or would it change as more and more thread unspools? It's a great little puzzle that builds right on what we just did. Thanks for tuning in.